Welcome back to Compiler Construction. In today's lecture, we are finally arriving at the back end. And so today we're going to talk about code generation. So to give you an overview of the upcoming lectures on code generation, we will be mostly talking about how to select instructions that represent a given intermediate representation expression and how to allocate registers in order to efficiently enable program execution. This is part of the next lecture. So where are we now? We have parsed and scanned our program, we have generated internal representations, and we have finally arrived at some sort of representation that might look like 3-address code or a syntax tree, which is very much simplified. So we already have a fairly low-level view of the program, but still we are a bit above the level of the real physical machine, because currently our 3-address code, for example, assumes that there are infinite many temporary variables. So it features a memory model in which we have infinite temporary memory space available, which is of course not the case in a real computer. And also it is not specific in terms of real operations that are available in a given architecture we want to compile for. So instruction selection and register allocation will be almost our last two topics, the last two topics that are important to get your own compiler built. So we are going to talk about selecting machine-specific operations and mapping variables to memory locations. And in the final lecture of the course, we will talk about using static single assignment as an intermediate representation as an alternative to the 3-address code we've seen before. So when we are considering compiler backends, we know that the instructions of the low-level intermediate representation here, which is located somewhere here in this abstract view of compilation, are still not the same as the one of the target computer we're actually planning to generate code for. So we have all the different languages here on the left-hand side. So our source languages that might be C or Pascal or of course our VSL language. They all get compiled to some sort of high-level intermediate representation. This can be something like our abstract syntax tree, which then gets lowered to our low-level intermediate representation, which might be 3-address code. And this 3-address code now finally has to be lowered even further by generating instructions for a real machine, and that might be a 64-bit x86 processor, a 64-bit ARM processor, or maybe a RISC-V processor, or whatever you can imagine. So we can take a first very simple approach to code generation. This is a very straightforward solution, and this actually is just more or less a table that maps every low-level intermediate representation instruction to a fixed sequence of assembly instruction. For example, we have a RISC-like machine on the right-hand side. This is not representing a real physical machine, but just giving you an example. And we have a 3-address code instruction here on the left-hand side, like x equals y plus z. And we could translate it into 4 instructions on the right-hand side. So if we could first load our operands here, so we could load our first operand y into register 1, then we could load our second operand z into register 2, then we could perform the operation on both parameters which are loaded in R1 and R2, so we could add them together. Here this is an add command that actually places the result in the first register here. So if I add R1 and R2, this actually adds the value of R2 to R1 in our example here. And then finally we have to store the result back into the variable on the left hand side, so we move the value in register 1 to wherever x is stored in memory. This is simple, this works, this generates code that's easy to understand, but of course it has a number of disadvantages. First, it has a large number of redundant operations. For example, we would always load values of variables into registers and store a value into register, a value from a register into a memory location afterwards. So essentially, we would copy data unnecessarily, and this in turn creates more memory traffic than necessary. So we want to find some ways to do it in a bit more optimal way. So let's look at examples for translations. When we translate instructions, we generally have multiple possible alternatives. So we are using a simple example here to demonstrate this. So let's assume we want to translate this instruction here. So assigning the J's element of array B to the I plus first element of array A using only the instructions given below. Note that these instructions are different from the ones we used on the previous slide, especially the order of operands differs, and also it's not a RISC machine here. So this is just to give you an example that works with just a small number of simple instructions. So first we have an add instruction that takes two parameters, and this adds the value of the first parameter here, register 2, to the value in the second parameter, register 1. So R1 equals R1 plus R2. So note the receiving register is now on the right hand side. We have a multiplication operation that just multiplies the register value in register 1 by a given constant C. So that's the instruction on the right hand side here. We have a load instruction that dereferences the address in R2, so loads a value from memory addressed by R2 into register R1. So that would be the equivalent C instruction on the right hand side here. Accordingly, we have a store instruction that stores the value of register R2 into memory at location R1. So this would be, again, the equivalent C instruction. And then we have two instructions which usually don't show up on a RISC machine, but might show up on something like an x86 CISC system. So we have a move memory instruction that actually copies memory from one memory location to another. So we copy the contents of memory location R2 into memory at location R1. And we have an extended indexed version of this. So here we have two parameters at the source address here. So we add the values of R2 and R3 together to give the address to be dereferenced. And we copy the contents of this memory at a location addressed by the sum of R2 and R3 directly into memory at the location indicated by register R1. So to continue with our example, we just assume that everything here is represented by 8-byte elements and that we have certain conventions here. So register RA, so just any given register with an index A holds the address of variable A. Register RB holds the address of variable B. Register RI holds the value of I. And again, register RJ holds the value of J for our instruction, which we have again here, that we want to translate. So what do we have to do to translate this instruction here? So first we need to obtain the value on the right hand side, so array B and the J's element of that array. So we need to find the address of that J's element of B in memory. We have to load this value in memory. Then we have to find the address of the array element on the left hand side, A of I plus 1. And finally we have to store the value that we've just loaded here into that memory location. So let's look at a first simple translation of our 3 address code to do this to real machine instructions for our example architecture. So our 3 address code to perform our copy operation could look like this. So first we need to find the address of the J's element of B, and we have an index here 0, 1, 2, 3 as usual for arrays, and we have said that each of these elements is 8 bytes long. So the first thing we have to do is we have to multiply our index J into the array by 8 to give us an offset from the base address. Then we have said that that B is our base address here, so we have to add our offset we just stored into T1 to the base address in B and store this in T2. So this would be the first operation here, getting the address of the J's element of array B. And then we have to load this element into, for example, a temporary register here. So in 3 address code, this would look like we have the address that we've just calculated in T2, so we have to dereference that address here and store the value of that we just read from memory at location T2 into a new temporary variable T3. Then we have to calculate the address of the I plus first element of array A. So this works very similar to what we've done before for array j. Now here we have I plus 1 as the index. So first we have to actually calculate I plus 1. So we do this here and store this in T4. Then we have the index for our array A, and then we do the same as above. So we multiply that index by 8 and add this now to our base address of array A, and so we have our pointer in T6. So the final thing to do is now to store that value that we've just read from array B, which is still in T3, into memory at T6 here. So here we just write memory at location T6 with the value that we loaded into T3 a number of instructions above. And if we translate this to our example architecture, it might look like this. So first our multiplication here would be translated into multiplication of the index j, which is in register rj, by our constant 8. And then we add our offset rj, which we just multiplied by 8, to the address of b, which is in rb. So this adds the offset plus the base address to give us a pointer here. Then we can dereference that pointer here using a load instruction. So we have this address of the j's element of b in rb. So we can now load from memory at location rb into register r1. So we have loaded the value into r1. Then we do the address calculation here. So first we add 1 to our index I. So in our index I is stored in register ri. And then we multiply this index I again by the constant 8 and add this to our base address now of array A. So we add ri to ra. And finally, we have to implement that store operation here. So we store the value of r1, which we just loaded above here, into memory at location ra. Now, given the instructions we have shown as possible instructions for our example architecture, we could also do something different. So here's another possible translation. So our address calculations work as before. So we calculate the address of the j's element of array B first. Then we don't load any memory value from that address right now. We defer it until later. So the second step, we calculate the address of the I plus first element of array A. So now we have the element to copy from and the element to copy to. Their addresses are in registers RB and RA respectively. So now we could do this move memory copy operation to directly copy from the address RB into memory at the address RA. So this would essentially then implement those two instructions shown in red on the right hand side here. So one interesting thing we can learn from this is that even if the 3 address code we generated has these instructions here separated by another set of instructions, we can actually reorder and join instructions here if our data dependencies and an instruction on the target machine actually allows for this. But we're not yet finished. We have yet another opportunity. So here we could just calculate the offset into array B. So we multiply our offset j by 8 and leave it in register j. Then we do the offset calculation into array A and the address calculation of the element as follows, as before. And finally, now we can use this indexed move instruction to actually move the contents of memory at the address of base address of the array RB plus our offset we calculated above RJ. And we can copy this directly into RA. So this would yet be another opportunity which would join our 2 instructions here on the right hand side and would even actually combine this T2 instruction here we have to give us an even simpler implementation that uses fewer instructions than before. So what's the difference? Why should we actually care about this? Now we've seen not all instructions are created equal. So some instructions maybe on some machines are very fast, so they complete in a single clock cycle. Some may take quite a lot of time. For example, if you do a general integer division, that might take quite a lot of time. And if you just do an integer division by a power of 2, you could replace it by a shift instruction to perform the same operation in less time. Other instructions even have to be decomposed in a sequence of steps. They might take many more cycles, depending on whatever instructions your computer is actually supporting. So if we have a choice of different options for translations, we'd obviously like to have the one with the smallest sum of costs. Here, costs are actually represented by our execution time, but we could have different cost measures like energy consumption, for example, or for very memory constrained embedded systems where performance is not that important, we could also try to optimize for memory consumption of instructions. So in our examples we just analyzed, we've seen that partial instructions here, like our assignment 2T3 and our assignment into memory at location T6, aren't necessarily adjacent. So for example, this move instruction here could actually represent these two instructions and actually also the one including the index with T2 above, because this addition is done implicitly by MoveX. So what we want to achieve is we want to enable our code generation to actually be flexible about choosing these instructions, and we do this by looking at a tree representation in different ways. So if we continue looking at our example assignment here, the 4 steps we have to take can actually be written as a tree. So here on the right hand side we calculate the offset into array B. So we take our index j into array B, multiply it by constant 8, add this to our base address of B, perform a load operation here, and on the left hand side we calculate the offset into array A. So first we have to add 1 to I, then we have to multiply this index I plus 1 into array A by our constant 8 again, add this to our base address of A, and then finally we can load the value from the j's element of B and store it into the I plus first element of array A. Now instructions we generate from this tree don't have to be related to just a single node or a single subtree of our expression tree here. Instead, instructions can actually be tiles, so just more or less connected arbitrary subparts of our graph. So a tile is just a subtree of a particular pattern. For example, this move M instruction we have seen in the second example that moves memory from location R2 into memory at location R1 would represent a combination of this store and this load instruction, whereas the parameters here, R2 and R1, would have to be provided by our subtrees here, so by a different set of instructions. In turn, if we take a look at the third example, so our MoveX instruction, we know that this address addition, so adding the source address offset to the source address base address here, is also done by this MoveX instruction. So this MoveX instruction would in turn represent a different subtree of our tree here. So it would not only perform the store into R1 and the load, but it would also perform this addition of the base address with the offset inside that array. So this gray area here would be the subtree to represent our MoveX instruction in our example. So for generating code, we can perform tiling of our tree here. So a given instruction selection covers our tree with disjoint tiles. So if we go back to our MoveM example, MoveM would represent the store and load operation here. Then we have our other operations calculating the offsets. So this j times 8 would be a mul_c operation here. That gets then added to the base address of B, which is then passed to MoveM, and the other parameter here, RA, is actually obtained by first incrementing I by 1, giving the new index for array A, then multiplying this by 8 because every element is 8 bytes in size, finally adding this to the base address and providing this as the other parameter for our MoveM instruction. And so if we do a bottom-up walk of our tree, we could actually get to this instruction sequence here, which would implement our operation. So we start at the bottom right here by multiplying rj with 8. Then we add this to our base address here. giving the second instruction. Then we turn over to the left-hand side here. First implement our addition here as the third instruction. We add 1 to Ri. We multiply the value in Ri by 8. We then add the offset Ri to our base address in Ra. And finally then we can perform our top level operation, doing the move m from the address we calculated for the offset in array B into the offset in array A, so copying the value of this one offset in B over to the array A, which is given the offset I plus 1. So if we use different tilings for our instruction, we have different costs of our final generated program here. So if we use a store instruction to store the contents of RB into RA, we would have to perform an additional load here. We would have to do these calculations here, and you see the subtrees actually resulting in the generation of a single instruction are actually indicated with the same color. So the subtree here in yellow would be a multiplication instruction, the subtree here in light blue would be an addition instruction, and so on. And we see we have a separate load and a separate store instruction if we implement our code as in the very first example in this row. On the other hand, if we use the move fx instruction, we see that quite a lot of this here, store, load, and the addition to our base address B is already performed by our move x instruction. So we have a lower number of instructions, which can result, depending on your machine, in actually a lower execution time, for example. Now we've already seen that trees themselves are a good way to represent your code structure or your instruction organization, but we have already seen a better way, and this better way is actually used to eliminate common sub-expressions, and we have already seen how to do this. We convert our tree to a DAG, to a directed acyclic graph, which means we can actually reuse results of sub-expressions we have calculated. So to do this, we need to separate labels and annotations. We need to label nodes with variables, constants, or operators. Then we annotate nodes with variables that hold their value. And finally, we can construct the DAG from our low-level intermediate representation. So how can we do this? Now, the basic approach is that for each instruction in a basic block, we take a look at this instruction. So either we have an instruction x equals y op z in our 3 address codes, so we have 2 input parameters connected by some operator assigning it to a third variable here. Then we have to either create a node that's annotated with y, or we have to find one if it already exists. We have to do the same for our second operand here for z. Then we have to either create a node labeled with the operand that has the operands y and z, or if it already exists, so if you already have an expression that calculates y op z, we have to find it and can reuse it. Then we can remove the annotation x from everywhere, and because we are overwriting the value of x here, we add the annotation x now to the node representing the operation. On the other hand, if the instruction in our basic block is just an assignment instruction, x equals y, then we have to find, if it already exists, or if it doesn't exist, create a node that's annotated with y, and also add the annotation x, because after this instruction, both values are identical, obviously. So let's take a look at another example. So here we have 3 address code again. So we add y plus 1, assign it to t. We add y plus 1 again, assign it to w. So here you see we have some sort of redundancy, obviously, for the sake of our example. Then we multiply our intermediate value t by z, giving it copy it into y. We increment t by 1. We multiply t and y, assigning it to z. And finally, we assign the value of z to the value of w. So let's start at the first instruction, t equals y plus 1. Nothing exists so far. We are at the start of our basic block, so we have to create a node for variable y. We label it with y because that's what gives us the value of y. We have to create a label node 1 just giving us a value of 1. And then we have to combine both with our operator plus here. So we have a plus operator combining y plus 1, giving us here the label, the annotation t, which is the result of this operation. Now our second line of code already gives us an optimization opportunity. So we've seen we either have to create a node or we can find a node. So of course, obviously first we try to find a node before we create one. So here we try to find a node y. It's already here. We have node 1. Well, that's already here. And then we try to find an operator node plus that already combines y plus 1. And hooray, it's obviously here. So we are not changing the tree at all. The only thing we are changing is the annotation to the operator. So now in addition to generating a value for t, this also generates a value for variable w. So in our next instruction, we multiply z by t. So we either create a node or we find a node for it. So z is not yet existing, so we need to create a node for z and annotate it with z. And then we need to find a node for t. Well, that's already here, annotated. So we add another operation node, a multiplication node that combines z and the value of t, which is identical to w, and annotate this with giving us the value for variable y. In our next operation, we increment t by 1. So essentially what we have to do is we have to find a node giving us the value of t, which was this plus node here before. And we already have a node that gives us a 1. So we move the label, the annotation t, up to our new operator here that adds the former value of t plus 1, giving us the new value of t. In our next step, we want to multiply the values of t and y. So again, we look for annotations of operator nodes or value nodes giving us t and y. And of course, we have them here, t on the right-hand side, y on the left-hand side. So what we do now is we add a new multiplication node because we can't find an operator node already giving us t times y. So we add this new multiplication node and annotate this to give us the value of z. And finally, we have just a simple assignment node, w equals z. So we just have to find the node that is annotated with z and have to add another annotation that says that our value of w is also generated by this operation. And so we have our simplified DAG here, which takes fewer instructions than the equivalent tree. So here again, we have performed a simple optimization for the code we want to generate. So this was a simple introduction into instruction selection and the theory how it works. We'll give a detailed introduction into how instruction selection works for x86 in the Q&A session, and you'll also get some annotations in the slides related to that Q&A session, and we'll also give tips on how to get this to work not only on x86 64 Linux but also on Mac OS X machines. So in our next lecture we'll take a look at register allocation, and then finally we'll take a look at static single assignment and SSA optimization. That's all for today. Thanks for listening. Until next time.